Hey there, chemistry team. Your chemistry coach is coming at you with some more redox. All right, what's going to happen in general chemistry is you will probably run into redox reactions occurring in aqueous phase. You got the little parentheses AQ, and you go, oh crap, this is going to be a lot harder. Right? If it's not an aqueous solution, pretty easy to predict your products and balance these things. Not so much. Some of the most complicated chemistry I've seen at this level involves redox reactions in aqueous solution. Yay for us. Here we go. Two basic things to remember. Well, one, don't try to do it on your own. Number one, if you see AQs in there, and you should be able to determine the oxidation number. So it doesn't matter whether it's an aqueous phase solution or not. You got your reactants. If you happen to know your products, just do the oxidation numbers of everything. And if they're changing up or down, you know it's redox. Now, if you don't have your products, depending on who your professor is, who's driving the car, right, who's running the show, some of them just skip this part and just give you, because it's a little too much for this level, they just give you the products. You got these two, here's your reducing agent, here's your oxidizing agent, boom, here's your products. You go, yay, how'd they get there? And they go, need to know information, right? But some professors like me go, no, in some scenarios, I want you to be able to know how to find that, right? Not everybody's going to, put your diapers on all the time and tell you what the products are. So I want you to know where to look and how to determine what your products are in some relatively simplistic fashion. So the redox table I'm going to give you is not going to be totally complete. But find a redox table, and a lot of times that'll help you predict your products. Very similar to acid-base tables we've used before, where if you have your acid, you can see on the next column it's the conjugate base, and if you have the base, the prior column's the conjugate acid, so you can predict what you form. It always goes from stronger acid-base to weaker acid-base. Same idea with oxidizing agents. We'll have oxidizing and an oxidizer reducer on one side, and if it's in equilibrium, you can have an oxidizer reducer on the other side, and you can actually have a reversible reaction in equilibrium. Oh, that gets crazy. Now, once you've identified your products and their states, then we can balance it. Please don't try to balance redox reactions in aqueous solution by inspection. Usually incredibly difficult. There'll be oxygens on the product side, but none on the reactant side. You're like, where did they come from? Right? So it gets a little weird. Please follow, depending who teaches your class, they may have different methods. We're going to be using the half reaction method. Later on, once you're comfortable with this, maybe in another semester, I'll let you use what's called the bar method, which is a little bit quicker. But I want to do the half reaction method so you can see each individual step and why we do what we do. I've taught at a lot of different colleges, and about every college I've taught at do the half reaction a different way. The half reaction method a different way. Whatever, you still get the products, okay? But we're going to walk it through. And where at the college we're at here, we're not a big fan of using H+, because it really doesn't exist in solution. We like to use the hydronium ion, H3O+. So the way we do the steps in our half reaction method introduce the hydronium ion in, when a lot of other colleges or places or professors would put an H+. And it's actually more common to see H+, because it does make it easier. Not quite as realistic, though. But anyway, we'll do the half reaction method. And if you're in my class, I have typed these out in a handout you can get from my website. So print that out, and we'll utilize that. Very likely I'll do the half reaction method in a different video, depending how long it takes us to go through the redox table. So let's do a little but show you how to use this redox table to predict products and whether reactions are going to be, favorable as written. Are they going to be more product dominant, more reactant dominant if they're in equilibrium or something like that? So let me erase this board, and if you got the redox table, go grab it. All right, so hopefully you were able to print out your redox table or find another source for it. It looks something akin to that. All right, looks a lot like an acid-base table. The acid-base table, we had acids here with strongest on top, and the conjugate base that it formed over here with the weakest on top. So it went from stronger to weaker acids, and then weaker to stronger bases. Very similar here. We have the oxidizer here with the strong, if you want to write in strongest on top here, and then they get weaker and weaker as they move down, and we actually have two columns. This is not a complete table in any way, shape, or form. And then we got the reducers here with the weakest ones on top and the strongest ones down on the bottom over here. So the oxidizer, this tells you if this is your oxidizer, that's what it will form in aqueous solution in most instances. And if you don't see any phase marks, it's probably going to be AQ in most scenarios. A lot of them don't put states at all, and you have to kind of determine it from experience and whatnot. So this is your oxidizer. See how the arrow points across? That tells you what it forms. And the stronger the oxidizer, the weaker its corresponding species it forms. So make sure you have one of these tables with you. We're not going to worry about this column right here at this level. But see where it says medium in blue? The A's and the B's and the NB's and whatnot? That's going to be important. So we'll talk about what those all mean in a second. But in general, a redox table is used to predict the product's form. If you know your... Woo! Total fumble. I rolled a 1. If you know your reactant, you can see what your product is. Okay? A lot like with acid-base tables. Also, we can determine if this is at equilibrium, if it's a reversible reaction. You can tell whether it's going to be reactant dominant or product dominant because the stronger species drive towards the weaker species. So your reducer and oxidizer on one side will be stronger than the oxidizer reducer on the other side, and will always drive from stronger to weaker. And so the weaker species will be the dominant species at equilibrium. Just like acid bases go from strong. So if both your acid and base are strong on your reactant side, that drives almost pretty much, we always say, essentially to 100% extent. So it's all products. But if they're both weak, now we got an equilibrium, but you can tell which one's going to be more dominant. So again, stronger to weaker, driven. Number 3, we can tell if the mediums match, and that's the mediums here. So if I have a reactant where the reaction's occurring in acidic medium, but I have another one where it's going in basic medium, those don't match. You can't have one reactant that only goes in acidic solution and one that only goes in basic solution. They're not going to go together. So they have to both be an acidic medium. You have to have an A for both of them or a B for both of them. They happen in acidic or basic. You'll also see Na means not acidic, so that could be neutral or basic, and Nb means not basic, so that could be acidic or neutral. So acidic and not basic would go together, right? So I could have an A with an A or an A with an Nb, right? Those kinds of things. So let's do a couple examples and show you how to predict them. But let me walk through the 3 parameters we're looking for and how to use this table real quick. Let me erase my board. All right, a couple things we need to look at for this redox table to work. And again, a lot of places don't teach this at all, and that's okay. Just takes you one level, one more arrow in your quiver, right? So a couple things we're going to look at. First is the arrows. The arrows have to point the correct direction. So every redox reaction will be an oxidizer plus a reducer. You cannot have 2 species from the oxidizer column. It'd be like 2 acids reacting together. Not going to happen. You can't have 2 reducers. It's like having 2 bases, right? It's not going to work out. So again, like you can't have 2 acids or 2 bases. You can't have 2 reducers. You can't have 2 oxidizers. You have to have one reducing agent that's donating electrons and one oxidizing agent that's gaining electrons. Okay, so you're going to have one from each column. So one reactant will be from your oxidizer column, one reactant will be from your reducer column. The reactants are always provided for you. Otherwise, how do you know what you're going to do? So here's your 2 reactants. Find them in the columns. One will be the oxidizer, one will be the reducer. So what I'll do is I'll look in the oxidizer column, strongest on top, and I'll just go down. I have my 2 reactants. I just go down until I find one of the 2. Boop! There, I got my oxidizer, okay? Once I find my oxidizer, then I'll go to the reducer column, because I can't have 2 oxidizers, and then I'll look for the other reactant that was provided. So I'll look all the way down here. If I don't see it, I'll go over here, right? Looking all the way through those. Here's how the arrows need to line up. Once you find your oxidizer, the arrow must point to the reducer, and that's your product, okay? So they have to point, or they can be reversible. So the oxidizer must point to the right to the reducer, which is your product. That would form that. Or it could go both directions in this case. If you have your reducer, the arrow must point the other way. So see this one, the chloride to the perchlorate, it doesn't point that way, so it can't. You can't have the chloride go into the perchlorate, but you can have the perchlorate go into the chloride. I'm trying to look in a mirror image here. Hey, this is a little better. So like the Mn2 plus is not going to form MnO2. It goes the wrong way. But I can go from MnO2 to Mn2 plus. If it's reversible, you can go both directions. Right? But here, like the H2O2 going to O2, H2S going to solid sulfur, you can go that direction, right? So the arrows must line up. So the oxidizer has to point to the reducer or be reversible, and the reducer has to point to the oxidizer or be reversible. If they both point, if it's pointing the wrong way, that reaction is not going to happen. So that's the first thing I want you to check for. All right, let's look at the next few things. All right, factor number 2 for a redox reaction in aqueous solution, other than the arrows lining up, is the mediums have to match up. And again, the mediums are this column in the light blue with the A's and the NBs and the NAs and the B's and all that fun stuff. They have to match up. So the reducer and the oxidizer. So if the oxidizer, if you pick this forming that, you look over here. So this one would be in acidic medium, right? And if I took a reducer, right, if I was going, or let's just say we take MnO4 to Mn2 plus in acidic medium, and I react MnO4 plus as the oxidizer to chloride ion as the reducer going to chlorine gas, well, that would happen to be, the chloride would be not basic, okay, which could be acidic or neutral. So those would match. MnO4 minus forming Mn2 plus in acidic solution matches with the chloride ion going to the chlorine gas with non-basic, which could mean acidic, okay? So the combinations, you look at the two and go, well, acidic matches with acidic matches with non-basic, basic matches with basic, B with B, and basic matches with not acidic, okay? But you couldn't do B with A. That wouldn't work. So if I was going to do, again, the permanganate ion going to manganese 2 in acidic solution with the permanganate as the oxidizer, and I wanted to combine that with something like the hydrogen sulfide ion going to sulfur, see that? So HS would be my reducer. That's in basic solution. Not gonna happen. You would just say no reaction. The mediums are opposite. Okay? But if the arrows point the right way and the mediums match, oh, we've got a reaction going on. Now the third thing will be, is that reaction going to be product dominant, reactant dominant? That'll be the next one. All right, last of the 3 things we got to look at, and then we can do some examples of predicting products, whether the reactions will occur, and whether products or reactants are going to be dominant. All right. Again, redox reactions and acid-base reactions always drive from stronger to weaker species. So the weaker side will always be the dominant side, to the point where it might be the reaction is complete or it doesn't happen at all. Depends. You need more information for that. But if the reactants are stronger, so on the left-hand side, the 2 reactants are stronger oxidizers and reducers than the products on the right-hand side, it will drive from stronger to weaker, boom, and it'll be very product dominant. Okay? If it's opposite, if the reactants on the left-hand side are weaker than the products on the right-hand side, it'll drive from stronger to weaker, in this case back to the left, and it'll be very reactant dominant, to the point where we might say no reaction occurs. Possible. Okay? And remember, oxidizers are strongest on top. They go stronger to weaker. So, you know, the permanganate ion is stronger than oxygen here, right? So fluorine, the strongest, that's the, you know, the top of the hill right there. So fluorine gas, with diatomic fluorine gas, is a stronger oxidizer than oxygen gas, or the copper 2 ion, right? Or, you know, whatever, anything below it. And reducers are opposite. The weakest ones here, strongest ones are down here. So a lot of these alkali metal ions and alkaline earth metal ions are very strong reducing agents, okay? Oh, right over here, these metals. Sorry, got the wrong column. So the metals are strong reducing agents because they love to give electrons, right? Those metals like sodium, they love to give electrons to become those ions and have a complete outer shell, right? So the stronger reducers are here, and they get weaker as they go up to the weakest reducers here. So in essence, if the oxidizer is above the reducer, that means it tends to be product dominant. If the reducer is above the oxidizer, it tends to be reactant dominant, because the oxidizers are stronger on top, reducers are stronger on the bottom. So if my reactant has an oxidizer here and my reducer is below it, that means the stronger ones are on the left, and it's going to drive towards the right. We'll show you. We'll do an example, and we'll look at the arrows, we'll look at the mediums, we'll look at which oxidizers are stronger and weaker and which way it drives, exactly like we did with acid-base reactions, okay? So we'll do 1 or 2 examples, and we'll be off to the races and done with this video. Sweet! All right. If you're not completely confused, give this one a shot, right? But I find the majority of students, the first time they're exposed to a redox table, are just like, my brain hurts. So many things to look at. And again, a lot of places don't even teach this. They just say, screw it, here's the products. And you're like, yay. As a student, you're like, yay, even though I don't know what's going on. You're here to learn, right? That's why you're paying the big bucks to go to college, man. You're to learn how to predict these things. Let's say we have this simple quiz question, right? Predict the products. Now, I'm being nice here. I'm telling you it's in basic solution. What are the products in basic solution? Hey, because we can't balance it if we don't know what the products are. Now, we're not here to balance it. That's a whole nother, ball of wax. What does that even mean? So we got the permanganate ion and the sulfite ion, not sulfate. That's SO4 minus sulfite. So I like to look, I don't know what's my oxidizer, what's my reducer, don't know. So I like to start in my oxidizer column, and I'll go down till I find either the permanganate ion or the sulfite ion. So I will look down, I'll go, oh, hey, look at that. I found it right away. But the problem is, do you see the A there? Not good. That's an acidic medium. This said basic. So we can't form Mn2+. It's a great indicator, by the way. I love permanganate solutions, beautiful dark purple. So we got to keep going down. That's the wrong medium. Oh, we can get confused. Looking for sulfite or permanganate. Oh, look at that. There's permanganate again, that little bugger. See how it's forming MnO2 in basic solution. One of the biggest boo-boos, B for boo-boo, is students don't look at the medium and they would give Mn2+ in this, but see, that'd be acidic solution, wrong thing. So if you're in lab and you're dealing with the permanganate ion, you'd best know whether you're acidic or basic solution, my friend, because you're going to get different components. If you get a bunch of little brown particles, you're like, uh-oh. So we're going to be forming MnO2 particles in basic solution. So MnO4 will be my oxidizer because I haven't found sulfite yet, okay? So that's going to form MnO2. Do you see that? So this is going to come around. That's going to form MnO2. And that'll be, and if you put an AQ there because it didn't have it, it's not going to be the end of the world. But from experience, I've seen those little brown particles floating around going, crap, I'm not supposed to see those. Now I'm going to look at my reducer column because I can't have two oxidizers. Let's look for sulfite as you scan your way through. You might be looking, I hate it when you're like, yeah, man, where's the darn thing? Sulfite is way over here. You see that in the reducer column? And that forms, see the arrow's pointing the right way, to sulfate in not acidic. Does that match? Not acidic means it could be basic or neutral, right? So my sulfite is going to form my other product. I'm going to get the sulfate ion in non-acidic solution. So this will give me sulfate. Boop. SO4 2 minus, and anything with a charge has to be AQ, right? So that's how we predict our two products. Now, the mediums match, right? This was basic. That was not acidic, so those match, right? This could occur in basic solution. Now, if I didn't tell you acidic or basic, this would be impossible because the MnO4 minus forms Mn2+ and acidic. That'd be a hard problem on a test. That's why I had to tell it was basic. We could balance this using the half reaction, but that's for another video. Now, do the arrows line up? So here's your sulfite ion. Yes, so it points over to the sulfate, and the permanganate points to the MnO2. So the arrows line up. That's good. Right? Mediums are favorable. So it's kind of like going on an airplane. Check, check. Is this, we got gasoline? Check. Is the tire popped? No, yeah, checked. All the passengers, luggage, check, check. I don't fly airplanes, so I have no idea what they check. But I do know we have to check a few things. We got to make sure the arrows line up. Boop. Mediums match. Boop. That means that reaction happens. Now we can tell which one's stronger, which one's weaker, and we can tell whether this is going to be product or reactant dominant. So let's take a look. So my MnO4, so this is my oxidizer, right? I'll go OA for oxidizing agent and RA for reducing agent, right? So the oxidizer, our MnO4 minus, is here, right? That's way higher than our reducer, okay? So that means this is a lot stronger. Or you can look, if we went the other direction, you could see that they're above each other. So see how the MnO4 minus is above the sulfate, right? If we're going the other direction, this is weaker, because it's lower on the oxidizer column, and this is stronger. And the sulfite, remember the reducers are stronger towards the bottom, so that's way towards the bottom. So sulfite ions are a pretty strong reducing agent. And then the MnO2 is way up here, which is weaker. So the MnO2 would be a weaker reducer than the sulfite, which would be stronger. And remember, these reactions always drive from stronger to weaker. So this is driven that direction. So I would call this product dominant. Or if you're just, if your professor's just saying, does a reaction occur or not? Yes, it would go from stronger to weaker. This reaction would occur as written. Yay! That's how you predict products. Not that big a deal. Let's do one more and call it a day. I won't go in as much detail on this next one. Foist! See if you can do this on your own. So we're going to take, now this says predict the products, but I don't tell you if it's acidic or basic medium this time. So you have to see, are they both acidic, both basic, or if one's A and one's B, that reaction is not going to occur. So we got the dichromate ion in aqueous solution and the chloride ion in aqueous solution. So pause this puppy and see if you can predict using the table what your two products are. What's the reducing agent? Which of these is the reducing agent? Which is the oxidizing agent? Predict the products. Make sure the arrows line up in the right direction. Make sure the mediums match. And then tell me whether this would be product or reactant dominant. And a lot of times if it's reactant dominant, we'd say the reaction wouldn't occur. And if it's product dominant, it would occur. Yeah, that's simplifying it, but give it a shot. I almost paused it myself. I don't need to pause it. All right. I'm going to look for my oxidizer first. So I'm going to take a look at my oxidizer column and try to find dichromate or chloride. It's chlorine. See, the chlorides are in the reducer column over here. Was that dichromate right there? I can't. Yep, there's dichromate. Okay, and I'm going to make sure I don't see it anywhere else. Remember the permanganate, we had acidic and basic. So if you look the way through, I don't see dichromate again anywhere. So it looks like that's our only option. So the dichromate forms the chromium 3 ion in acidic solution. Right? That's the only option there. And then let's look on the reducer side for chlorides. I see a couple chloride ions there. I don't see it anywhere else. So that's my only options. Now here I've got chloride ion going to chlorine gas. And here I've got the chloride ion going to perchlorate, but see the arrow points the wrong way, so it couldn't be that. I cannot take dichromate to form chromium 3 and chloride to form perchlorate because the arrow goes the wrong way. They can't both point to the right. So it would have to be the dichromate forming chromium 3 in acidic solution and the chloride ion forming chlorine gas in non-basic, which could be acidic. So those mediums and arrows line up. So my first thing that's going to happen, this will be my oxidizing agent. And that will form the chromium 3 ion in acidic solution. All right? So the dichromate, where'd that little bugger go? The dichromate, arrow points to chromium plus 3, my product, in acidic solution. Now let's look at our chloride. Can't do this one, the arrow points the wrong way. So the chloride ion is going to form chlorine gas in non-basic. So this is going to form, so this would be my reducing agent, and that's going to form chlorine gas, and that was, what did it say, not basic? Yep, not basic, right there. So would you agree the mediums match up, right? Acidic and not basic could be acidic. Arrows line up, so this reaction occurs. All right, so arrows line up. The mediums match. Now let's see which one are the stronger ones. So they're pretty close to each other, but see the dichromate, right, is below the chloride. So the dichromate, if you look over here, is below the chlorine. So the dichromate is weaker than the chlorine. Right, so this is my weaker oxidizing agent. This would be stronger. So if I was going in the other direction, right? And then the chromium and the chloride, right? So here's your chloride, right? Oop, that one. And then the chromium 3, right? So the chromium-3 is below the chloride. The lower on the redox column, the stronger. Right, so this one's stronger. This one's weaker. So it dries from stronger to weaker. So this would be reactant dominant. Or in some places, if you have a professor that doesn't do reactant product dominant, they just say, yes, the reaction occurs as written from reactants to product, or no, it doesn't happen. We could have possible no reaction. Just depending who you have and what you're doing. There you go. That's how you do it. And then, of course, we can balance it. But that'll be our next video. Oh, put your seatbelt on. It's going to get nasty.